This is Unit 5, Lesson 1, Video 4 for Chemistry 2. We are going to be looking at two example problems dealing with equilibrium, writing equilibrium expressions, and calculating Kc. So for this first example, if we look at our reaction, it says, number 1, write an expression for Kc. Well, that K value is based on concentration. So to write an equilibrium expression, we're going to use our products over reactants, each one raised to its stoichiometric coefficient. So we would write Kc is going to be equal to any of our products, and in this one we only have one, NH3, so it's going to be brackets around it, NH3. And since there's a coefficient of 2, we're going to put a 2 there as our exponent, over any reactants that we have. So we have N2 to the first power, and you don't have to write to the first, you can just leave it blank. And then the concentration of H2 to the third power, since we have a coefficient of 3. So for any values that we are given or calculate for molarity of these substances, we can just plug them into this expression and we will get the K value. So number 2, it says calculate Kc at 500 degrees Celsius if we're given those amounts of N2H2 and NH3 in a 5-liter container at equilibrium. So we're given moles and a liter, so we have to calculate molarity. So what we're going to do is we are first going to calculate the molarity of each one. So N2, we have 3.01 moles over 5.00 liters, and that is going to be 0.602 molar. We are going to calculate the same thing for H2. So we have 2.10 moles over 5.00 liters. That's going to give us 0.420 moles. And then we have NH3, and that's going to be 0.565 moles over our 5.00 liters and give us 0.113 molar. So now all we have to do is put these values into this equation. So Kc is going to equal 0.113, which is our NH3 concentration, squared over N2, 0.602, times H2, 0.420 to the third. So you can pause the video, calculate this, and come back and see if you got the same thing that I got. So when you calculate this, you should get 0.286. So I kept 3 significant figures in all of these. I'm going to be doing that in all calculations, going with the lowest number of significant figures. So based on that, we can look at this value, which side of the reaction is favored. If you remember back to the first page of notes in this note packet, we talked about it kind of being like anything below 0 and anything above 0. Well, this one is below 0, so we say it favors the reactants. That means that there's more of this at equilibrium than there are products. So it can favor the reactants or it can favor the left. Either one is a proper way of saying it. And remember that K does not have any units. So now we can look at our second example on the next page. And with example number 2, here we're given another equilibrium equation. And this time we're given a Kc value. So 1.84 times 10 to the minus second. And we're told at equilibrium, H2 is equal to I2, and they're both 0.0250 molar, and we want to find HI at equilibrium. Well, we would have to write a Kc expression. So our product is HI and it has a coefficient of 2, so that is now our power, over the concentration of H2 to the first times I2 to the first. So products over reactants, each one raised to its stoichiometric coefficient. Now all I have to do is put in the values and solve for whatever I'm looking for. I'm looking for HI. So our Kc value is 1.84 times 10 to the negative second is equal to concentration of HI squared over 0.0250 times 0.0250. Now, there's a couple different ways that we could solve this, but if you look, here we have a squared factor, and this is times itself, so this is squared in the bottom. So we could take the square root of both sides and get 0.136, which is the square root of 1.84 times 10 to the minus second, is equal to concentration of HI over 0.0250. Then we can multiply 0.0250 by each side, and we get HI's concentration to be 0.00339 molar. Don't forget, if it's a concentration, it has the units of molar on the end, capital M. You should now work on equilibrium constant worksheet number 1.